Good morning, good afternoon, or good evening. This is going to be a full paper workthrough of the May 2024 AS Further Maths Paper 2, the Mechanics section. So this is ideally going to give you a view on how you should be tackling such papers and give away some of the ideas and useful thought processes to tackle one of these effectively. So we're going to dive straight in. I do have my formula book to the side. I have my calculator ready to go, and all that remains is to turn the page. So we're straight in with our multiple choice questions. Here we have an elastic string, we have our modulus, which is our lambda, our natural length, and we have the extension being 0.5. We want to find the elastic potential energy. We need to remember our formula. EPE is lambda x squared over 2L. So in my calculator, that's going to be 20 times 0.5 squared. Just double checking the units are all correct. Of course, if something's in centimeters, we need to turn it into meters first. That's going out as 1.25. State the dimensions of impulse. Well, impulse is a force times time. You can also think of that as a change in momentum, so it's the same units as momentum. Force times time, or force is a mass times acceleration times time. So I'm thinking of the dimensions. I've got a mass, Lt to the minus 2 from acceleration, and a t from the time. It's going to be mLt to the minus 1, which also is exactly a mass times a velocity, which is what you'd got if you did change your momentum instead. A cyclist travels around a circular track. Circular, I'm thinking about my circular equation formulas at a constant speed. Find the angular speed. So I want omega, and I've been given the radius and the speed. I've quoted my formula wrong. V equals r omega. Well, omega is V over r. So I'm doing 8 divided by 20, which is 0.4 radians per second. And a little awkward if I did it the other way around. I wouldn't have got an answer there at all. Into our proper questions. This immediately looks like energy. A ball is projected vertically upwards with that speed. Initial kinetic energy is half mv squared. That's a half of 0.5 times 10 squared. Now I should do that in my calculator, and you should definitely do so as well, but I cheated slightly there. Assuming that the weight is the only force, use an energy method to show the maximum height is approximately that. So it's a show that question, so we know what we're aiming for. Because gravity is the only force, that says that our kinetic energy is converted into gravitational potential only. So 25 joules, I realised my J up there didn't look very much like a J, it looked more like a 5, equals 0.5. Question told me to use 9.8 times H. Because it's a show that question, I'm going to make it really obvious to the examiner what I'm typing into my calculator. 25 divided by 0.5 G is giving me 5.102, etc. Again, because it was a show that question, I'm going to make it really obvious that I haven't just written down the answer that they've told me. I'm going to write down more accuracy first. It does continue. A student conducts an experiment to verify the accuracy. They observe a height of 4.4 and concludes this height difference is due to a resistive force. Yeah. Find the total work done against R while the ball is moving upwards. So now the kinetic energy has converted into our GPE plus the work done. So that energy we had before, the 25, is now equal to the mgh 0.5, that's 9.8, now by 4.4, plus the resistive force, well, work done is force times distance. Well, we've overcome this resistance for 4.4 meters. So 4.4 R equals 25 minus the other stuff, which is positive at least, 3.44. And actually, I've done more than I needed to. The question wanted the work done. Well, the work done is that total 4.4 R, and that's how many joules of energy. Total work done against R. I want the whole of that term instead. Using a model that assumes R is constant, I did accidentally assume that above, find the magnitude of R. Well, now I'm doing that final step. The work done is 4.4 R. Divide that by the 4.4. And we're getting 0.781, and the 8 ones repeat. Like in the first part of the question, I am going to round that to 2 sig fig, because my 9.8 was to 2 sig fig as well. There's a force in newtons. Comment on the validity of part 2. Well, resistance is rarely constant, but we've had to assume that for this model. So comment on validity, unlikely to be valid, as resistance is rarely constant. Normally it's proportional to the velocity, or even sometimes the velocity squared, depending on the model you're using. Question 5. Power this time. Kang is riding a motorbike across his straight horizontal road. It has a maximum power of 75,000 watts. The maximum speed is that. When the speed is V, the resistance is kV. Find the value of K. Now this is 4 marks, which seems reasonable for the amount that we have to do. Well, at max speed, we have no acceleration. So maximum speed implies that the driving force is equal to the resistive force. So the driving force is equal to kV, but now V is 50. And now if we use our power equation, power equals force times velocity, so that's 75,000 is the 50k times by the velocity of 50. All of this is happening when it's at that max speed. So let's do the 75,000 divided by the 50 squared, and k is 30, which really doesn't feel like a lot of work for 4 marks, but we've used 2 different equations, we've used several different mechanical concepts. Question 6. Kepler's third law of planetary motion is given by that. T is the time, I is radius, m is mass, g is gravitational constant. Use dimensional analysis to find the dimensions of g. Well, that's going to be, we need to be a little bit careful. First thing I'm going to do is make it obvious to the examiner that I know my dimensions. So T is in time, T is in T, R is in L, the mass is in kilograms in capital M. So now the equation is saying the dimensions of T are equal to, now I'm thinking, do I want to, I'm going to rewrite this first as the individual powers. So this is 2 pi r to the 3 over 2, g to the negative a half, and m to the negative a half. I feel like that's just going to make my life a little bit easier. So this is then going to be dimensions of r to the 3 over 2, dimensions of g to the negative a half, dimensions of m to the negative a half. Notice the 2 pi's disappeared. Numerical constants have no units. They do just disappear. So let's turn everything into its stuff. And the awkward bit is going to be the g. I don't know what that is, so I'm going to keep it in its square brackets to the negative a half. Well, then let's throw that over. So g to the half, the dimensions of g to the half. And I'm going to put these in the normal order. And I'm throwing the t back over as well. So finally, if the square root of the units of g is that thing, then the units of g are just the square of that. That is negative 2. So I just doubled the powers. Now, if you know anything about the kind of gravitational formula, you might be able to interpret this as making sense. This is kind of meter cubed per kilogram per second squared. Maybe that's exactly what that g should naturally be measured in. Of course, you don't need that knowledge for this course. That's what the mathematics has told us. Question 7. A single force acts on a particle on a smooth, straight horizontal line. The force acts in the direction of motion. At time t, F is given by that. Find the impulse. Okay, well, impulse is normally force times time. And that works if the force is constant. However, if the force is non-constant, this turns into an integral. So we're actually integrating between 0 and ln 8, those being my time boundaries. So this is the integral between 0 and ln 8, 6e to the t plus 2e to the 2t. And we integrate each of those. Key fact being that the integral of e to the t is still e to the t. Integral of e to the 2t is a half e to the t, e to the 2t. So those 2's cancel. You can check that by differentiating back between ln 8 and 0. Let's sub them in. 6e to the ln 8. And probably I should have checked the number of marks before this, because I think I could have cheated. Subtract 6, or e to the 0 is just 1. So that is going to be, well, e to the ln 8 is just 8, so that's 6 times 8, plus 2 ln 8 is ln 64, then the ln and the e cancel. Subtracting the 7 is 105. And yeah, as expected, it's only 2 marks. So this question, we probably should have just put that into our calculator. Just stick that straight into the calculator exactly as it's written. We don't need to know any of the integration facts at all, and we can just get our answer. Part B. The particle has a mass of 2, and it's at the beginning 5 meters per second. So this is using the other formula for impulse, which is the change in momentum. So we've already worked out our impulse as 105. We don't know the final velocity, but we do know the initial velocity. So this is a nice simple solve. And v is going to be 57.5 meters per second. Really gained quite a lot of speed there in 3 seconds. And then again, I shouldn't be too surprised. It is being impacted by an exponential force. They get very big very quickly. Question 8, our collisions question. 2 spheres of equal size, same direction, mass m, 4u, mass 6m, speed u. Everything is given in the question, in the picture. Find in terms of m the total momentum before the collision. Well, momentum is a vector quantity, is mass times velocity. So for A, that's going to be 4um. They're in the same direction, so an extra 6mu. So it's a total of 10mu. So now we need to find the speed of B after the collision, being that thing. Well, we've got 2 formulae. Now, the first thing we should do is label on to our picture what we think is going to happen. I'm going to put them both going in the same direction. And if I was wrong, then one of them will come out negative later. So let's set up our two equations. Our first is our conservation of linear momentum. We already know that our momentum before was 10 mu, so that's going to equal our momentum after mva plus 6m vb. Cancel out the m's, 10u equals va plus 6 vb. There's one equation. Our second equation comes from Newton's experimental law, E equals sep over ap. So the speed of approach, they're going in the same direction, so I'm going to subtract them, is 3u. A is catching up at a rate of 3u. I multiplied that up, so 3ue is the speed of separation. These are in the same direction. I'm going to do the faster one, which will have to be vb, take away va. So now I've got two equations. I want vb. I can do that quite easily by simply adding the two equations. Adding them kills off VA. I'm getting 7 VB. That's already making me happy because I've got a 7 in my answer. And adding on this other side, 3EU plus 10U. I'm going to factor out the U, mostly because, again, I've looked at the answer. I know what I'm aiming for. So therefore, VB is exactly as the question wanted. I expect the next part to find VA. It's not, but we do need to do it. So after the collision, VA moves in the opposite direction. Now notice what I said already. I put the arrow going to the right, but now I've been told the arrow is going to the left. So when I work out my VA, it's going to be the negative of it. I need to find the VA first. I'm just debating whether to use equation 1 or equation 2 for that. I think I'm going to use equation 2. So if I rearrange equation 2 to make VA equals, it's going to be VB minus 3EU. What was VB? 3EU plus 10. 3EU plus 10U over 7. Well, that was a show that of the question above. I'm going to also write this one over 7 as well. So therefore, VA, the 10U doesn't change, but then I'm subtracting 18 EU over 7. And now we bring in the opposite direction. So my arrow was wrong, which means this expression must be negative, i.e. 10u minus 18eu is negative. I can cancel the u's, so that's 10 is less than 18e. E is greater than 5 over 9. Now we need to remember to be not to just leave it there, because we have another restriction on E. E cannot ever exceed 1. So my final answer is 5 notes is less than E is less than or equal to 1. You do get a mark for remembering that less than or equal to 1 condition. Being less than or equal to 1 is actually a conservation of energy requirement. Question 9. A small coin is placed on a rough horizontal turntable, as shown. The mass of the coin is 3.6 grams. A little awkward that it's in grams. I need to be able to turn that into kg if I do anything clever with it. The distance OC is 20 centimeters. So I already need to convert that into 0.2 meters. It rotates around the vertical axis through O with omega radians per second. Draw a diagram showing all the forces on the coin. So here's my coin. I'm going to have its weight, 0.0036. I have put the right amount of noughts in there, G. I'm going to have the reaction force going upwards because I'm touching the table. Now, if we think carefully about this coin, if it's spinning on a turntable, it wants to slide outwards. To prevent it from sliding outwards, you have to have a force going inwards, and the only such force that could possibly be here is the friction. Part B, the maximum value of friction is 0.1 newtons. When the coin does not slip, find the maximum value of omega. Well, if I'm going for the maximum value of the rotation, I should use the maximum inward force as well. So this is now going to use our force equations. We've either got mv squared over r or mr omega squared. Mr omega squared seems like the one that's relevant here. So that's 0.01. The mass times the radius times omega squared. We've got lots of small numbers because they're all small. It's going to turn out relatively normal. And you be careful if you're trying to type this into your calculator. I want to multiply first and then do the 0.01 divided by the thing. And that's coming out as 125 over 9. That both is promising and not, because it almost square roots perfectly. The numerator is 5 root 5 square root of the denominator is 3. So almost perfect, but then again the question did tell me to put my answer to 2 sig figs. For good exam technique, I'm going to write down a few more first before I round, just in case somehow I manage to round wrong. They still can see I've got the correct answer and I get all the method marks at least. A quick read through. I haven't done anything, I haven't missed anything out. There are no other forces on the coin, so happy. State one modelling assumption you've made in part B. So what else did I assume when I found the maximum value of omega? And some of these are already written in a question. You should try and avoid writing an assumption that's already there. The classic is air resistance. We've kind of assumed that there's no air resistance. That will cause maybe it to slip in a different direction, or at least have the friction pointing in a different direction. But the best that I'm going to go for is we've assumed that the coin is small enough that the radius is indeed what the radius is. Assumed the coin is small enough so that the radius of motion is 0.2 meters. You can imagine if we had a very large coin in relation, that even if that bit there appeared to be 0.2, the actual radius of motion would be quite a bit bigger. It'll be whatever 0.2 plus the radius is. And if you're only 20 centimeters, if you've got a 1 centimeter diameter coin, that's going to make a sufficient difference to some of the model. I'm not the most satisfied with that answer, mainly because the question already said it was a small coin. It didn't say it was a particle, which is basically what my assumption here was. I'm assuming it's a particle, so that it's small enough. Probably I should use that word in the answer. And there's probably at least another reason or two in there, which I can't think of right now. That is the last question, however. Hopefully you found that useful. If you have spotted any errors that I've made, please do pass them to me. And I hope you found this at least a little bit useful in the kind of thought processes while you're tackling these questions. Good luck and goodbye.